All right? Okay, so doing this limit, how are you going to go after this?
I'm going to say it's pointing out what it is.
Okay, so what is it? You let x approach 2, top goes to 0, bottom goes to 0, 0 over 0, algebra, trick, something, right? Algebra?
Algebra.
Okay. What algebra?
Difference
Difference
of squares on
of squares on top, cancel a factor. So I'll write the next line. Limit x approaches 2 from the left. All that's left when you cancel out is x plus 2, right? That's all that will be left.
Right.
And then on this side we have 4a plus 2b plus 3. And now let's go ahead and let x approach 2. And what happens if we let x approach 2 there? The left side becomes 4, right? All right, so I'm out of room down here, so I'm just going to wrap it back up here. Here's where we are. The left side, the limit actually just became 4, and we have 4 equals 4a plus 2b plus 3, right? That's where we are. So to recap, we looked at this and we said, we're supposed to find the A and B that make it continuous everywhere. We said, okay, well, there's only 2 places it's not continuous, at 2 and at 3. At 2, we said, okay, let's try and force it to be continuous at 2. So we figured out what the function's value was there. We took the limit. We had to identify which part of the function we were going to work with. We found that, and at the end of it all, we say that 4a plus 2b plus 3 must equal 4. That equation we cannot solve for a and b, because we only have one equation, and we have 2 unknowns. But we still haven't talked about continuity at 3 yet. Okay, so we're going to just put this on the back burner now, and we're going to go talk about continuity at 3. And try and keep this all on one screen. Continuity at x equals 3. All right, so Jasmine, there you go. So what is the limit definition of continuity of a function at 3? So what am I going to write down here? X approaches 3 of f of x equals f of 3. Okay. Now, I'll let you continue. The right-hand side is usually the easier one to do. What is f of 3? So which of these 3 are you going to plug into? Top, middle, or bottom? If you're asked to plug 3 into the function. Bottom, because of that little symbol right there, right? So you're going to replace x with 3 now, and what do you get when you replace x with 3 right there? No, just forget this side, just this side, sorry. Just this side. 6 minus a plus b. Okay, good. All right, so the right side we're trying to match this piece up now. So now moving on, the left side, Omar.
You input 3 to the middle piece, the ax squared.
The limit, right? So we're going to do the limit here as x approaches 3, and you're going to go into the middle piece. And can you kind of help explain why you're going to go into the middle piece?
So the interval notation says x is less than 5.
Yeah, x is less than 3. So we're trying to get close to this point, right? So we want to be using the middle piece. We don't want to be up here. This is nowhere even near 3, right? So we want to be using the one that's close to 3 but not at 3. So we use that one. And that limit, technically, we're coming in from which side? It's still from the left, right? Because remember, we had our 3 pieces. It was like, I don't know. It was like 3 pieces like that. So we're fixing the right end point here. We're going to be coming in like this. So we should have a little minus on that 3. Now, Omar, when we take that limit, does anyone have any questions about why this went in here? Okay. So, Omar, what's that limit? X is approaching 3. Do we have any problems with that limit like we had over here where we had to do algebra? No, we just plug in 3, right, for x. So what do we got here? 9a plus 3b plus 3 must equal this side, right? There. And now what we have is a second equation with 2 unknowns. So we have two equations, two unknowns, and then how do we solve that? System of equations. So you could do, you said matrix in the beginning, and you could use the matrices for this, but I don't think we need a matrix. So here's where we are. We have two equations, two unknowns. I'm going to write those equations down. So here's my first equation, right, from earlier. I'm going to write that down. Now watch the way I write it. 4a plus 2b equals 1. So what I did is I got all the variables on one side and all the constants to the other for that one. And now I'm going to do the same thing on this one. Let me get all my a's on one side with the b's. So what if I move all my a's to the left? How many a's will I have? 10a? How many b's will I have if I move everything to the left? 2 b's plus 2 b's. And then if I put my constant on the other side, what constant will I have over there? 3. And in college algebra, we all learned how to solve a system of equations like that, right? There are two methods for solving equations, systems of equations. What are the two methods? Elimination, substitution. Which method would you prefer to do on that one? Elimination, why? It's easiest here to eliminate the b's because one of them is 2b, the other one's 2b. So all you'd have to do is just scale one of these rows by -1 and then add the rows and back substitute. And so we'll do that. We'll do it rapidly. Multiply the top one by -1. We get a new system. -4a minus 2b equals -1. 10a plus 2b equals 3. And now we add straight down. So add down, add down, add down. What do we get here? 6a equals 2. And solving that for a, you get a is 2/6 or 1/3. So guess what, everyone? We know what a needs to be. And once you know what a is, you go get b. And how do you get b? Plug it into what? Whichever one. Doesn't matter. Okay, so now I'm going to go get b. And I'm just going to use the top one. 4a plus 2b was equal to 1. I'm going to replace replace a with 1/3. And 4 times 1/3 is 4/3. So 4/3 plus 2b equals 1. I'm going to subtract 4/3 from both sides. What do you get when you subtract 4/3 from both sides, Erica? Oh wait, Annika. -1/3. Good. 2b equals -1/3. And divide by 2. b is -1/6. All right. So here's what we're saying. We're done, right? We're pretty much done. We're saying that if we were to change this right here to 1/3, this right here to -1/6, this right here to 1/3, and that right there to -1/6, and we graph it, we should have a continuous function everywhere. We should be able to draw it without picking up our pencils. Any questions before I erase this? Because I'd like to see if we got the answer. No questions? System of equations? Have I told you all the story about that kid Gauss? No? Okay, I'll tell you all that in a minute. If I remember. Okay, so if we take, so we said if A was what? 1/3? And then if B, oh, whoa, what happened there? 1 divided by 3? What is all that stuff? Okay, let me try this again. 1 divided by 3. And then this one needs to be what? -1/6, -1 divided by 6. If I hit tab now, what happened? Oh, wait. Oh, I forgot to hit enable dynamic. I don't know what happened there. Whoa. I'm not sure what just happened, but we'll do it again. 1 divided by 3. Tab. And then negative 1 divided by 6. Yeah, there we go. Okay, so now it's a continuous function everywhere. I like those problems. It's a good test problem. Give you a piecewise function, 2 unknowns, because you have to understand what you have to do, and then you have to set up a continuity check twice. System of equations. Good. It's a good kind of, you know, wholesome problem. All right, we're done with continuity, I think. I'm just going to double check my notes here. Yeah. And before that, find the solution, intermediate value theorem. Yeah. Okay. We're done. Now, we're not done for the day. We're just done with this section. So I'll tell you the story, because we just did elimination, didn't we? We did a system of equations. And do you remember, like, in algebra, like, when you had 2 unknowns, 2 equations, elimination was very nice, but you could also have done substitution. But when you get to, like, 3 equations, 3 unknowns, elimination's better. And when you get to like 4 equations, 4 unknowns, elimination is definitely better. So, story. There's a famous mathematician named Gauss. Last name Gauss, I think first name Friedrich or something like that. Lived, I believe, in the late 1800s. Anyone heard of Gauss? Okay, so there's like a famous story that goes with Gauss. He was very bright as a very young child. His father was an accountant. So this is like late 1800s, right? No computers, right? So his dad was an accountant. And the stories go that he used to like sit in his dad's lap while his dad was doing his work. And he could add up these columns of numbers. Gauss could, the kid, could add up these columns of numbers before his dad could do it by hand. And so like they knew he was gifted. But the big story around Gauss is that something that happened to him when he was in first grade. Okay, so he went to class this one particular day, first grade, and the teacher that day presented the students with this problem. 1 plus 2 plus 3. So they all sat there and said, teacher was like, okay, what is that? And they were all, go ahead, you can answer. 6, okay, it's not a trick question. Okay, right? So 6, right?
What is this?
And then the teacher said, all right, so what's 1 plus 2 plus 3 plus 4? And the class was like, 10. And then it was like, very good. So the teacher said, today, class, what I'd like for you to do is I'd like for you to go ahead and do this and add it up all the way to 100. And so the story goes that the teacher was really doing this to kind of give the class like busy work. And the teacher just didn't want to have to teach that day or something. I don't know. But that's the way the story goes. And so within a few minutes, what happened was Gauss took his little chalkboard slate, because they used to write on little slates instead of paper. And he took his little chalkboard slate and he takes it and turns it over, puts it on his desk and sits there like this with his arms crossed, because they had like discipline and stuff back then. You know, they just sat there because you shut up and you just wait to be called on. So he sat there. So that was an indication to the teacher he was done. So the teacher went and turned over the slate, and what the teacher saw was this. S equals n times n plus 1 over 2. Okay, so before I explain to you what that is, before I get into more of the story, let me explain what it is. What that is a formula for adding up these numbers without actually having to add them up. So like for this first problem, here the n would be 3. And for this one, the n would be 4. Okay, so let's just check that the formula works. If n is 3, what does this become? 3 times 3 plus 1 over 2. And that's 3 times 4 over 2, which is 6, right? And it matches the answer. Okay, the next one would be 4 times 4 plus 1 over 2. And then that would be 4 times 5 over 2, which would be 10, right? Which matches the answer. And it works for every n. All right, so the answer to the Gauss's teacher's question was 100 times 101, right, over 2. So this is what? Like you could say that's 50 times 100. So I think it's 50-50. Someone can check me on that, but I believe it's 5,050. Do you see how the formula works? Okay, now let's get back to the story. So the teacher comes over, he turns over his slate, and the teacher sees that formula. And teacher says, who showed you that? So the formula was known already, all right? So it wasn't like Gauss was the first one to ever come up with the formula, all right? So the teacher was like, who showed that to you? You know, that's cheating. You can't use a formula. And Gauss explained that nobody had shown it to him and that he had just come up with it on his own, all right? So teacher, of course, didn't believe that, right? How is this little first grader going to come up with this formula on his own? So Gauss proceeded to explain it to him. All right, so you ready for the explanation? Okay. So here is Gauss's approach to this problem. Gauss said, let's say you want me to add up the first 100 numbers. Let's call that S. 1 plus 2 plus 3, all the way to 100, right? So we're going to have a bunch of stuff in here, and at the very end, we'll have like, I don't know, 98, 99, and then 100. Yes? Okay. So Gauss said, well, with addition, it doesn't matter what order I do this. So S is also equal to that sum written backwards. So I could go 100 plus 99 plus 98 plus dot, 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 dot. And when I got to the end, the last one would be 1, the one before that would be 2, the one before that would be 3. So far, we all good? Okay. So Gauss said, well, there's something else I can do. I can add these two together. Just add them straight down. So if I did S added to S, I get 2 S's. Yeah? Now, look at when you add these. Add them like these two terms first. What would that 1 plus that 100 be? 101. What would the next two be added together? 101. What would the next two added be? 101. All the way down. Okay. Slight little detour. Grade school, if you're taught to do 5 plus 5 plus 5 plus 5, they say, you know what, that's a bunch of BS, that's too much writing, we just go 4 times 5. Addition is repeated. Repeated addition is multiplication. It's the same thing, right? So when I do this, a shorter way of writing this would be to realize that I really am going to add up how many 101s. Careful. How many 101s am I adding up? Well, 1 of them, 2 of them, 3 of them, 100 of them, right? There are 100 of those. So 2S is 100 101s. But that's twice as much as I wanted. So I'm going to divide both sides by 2. So the sum that we're looking for is 100 times 101 over 2, which is that formula, right? Do y'all follow that? Okay, now I've lied to you. I've lied to you. Because Gauss actually didn't even show this. Let me show you what he showed the teacher. Because if I would have shown you this, I need to show most students this first, okay? So this is the way Gauss did it. I'm just going to make a slight little tweak. Gauss said, all right, you want me to add up the first 100 numbers. Gauss said, I'm going to do even better than that. I'm going to add up the first n numbers, okay? So what would be the number right before n? Well, whatever n is minus 1. Okay, what would be the number right before that? Whatever n is minus 2. Okay, what happens if you write that sum backwards? What's the first number written backwards? N. Okay, what's the next number? N minus 1. It's just this list backwards, right? Then n minus 2. Do y'all see that? Okay, and then Gauss said, I'm going to add straight down. Okay, when you add straight down, what do these first two give you? N plus 1. Plus, what's n minus 1 plus 2? N plus 1. What's n minus 2 plus 3? N plus 1. All the way down to the very last one, which is n plus 1. How many n plus 1s are there? Not 100. There's n of them. Right? There's n of them. So twice what we want is n of these n plus 1s. And then if you divide both sides by 2, you have your formula. So when you're doing elimination, right? We were doing elimination on that problem, and then when you're in college algebra, you learn elimination. It's actually called Gaussian elimination, because Gauss is the one who came up with it. All right? He's the one who proved you could do all the things you do in elimination. As you might imagine, he did many things in mathematics, right? This is just gives you a glimpse. I've always looked at this as a great example of genius. So how many of you follow his logic here? How many of you follow this explanation? I mean, a lot of you can follow this. Now, what separates geniuses from us, average people, I'm not going to say you're average, okay? I'm sure you're all geniuses in your own light, okay? But mathematically, coming up with this on your own in first grade, okay, that's genius, right? Can you appreciate that the way I appreciate that? What makes it so genius is that once it's explained to, pretty average people, it's like, yeah, okay, I get it. There's nothing crazy there. There's nothing too crazy, right? I can follow that. It's that bridge getting to it, right? Okay, so from now on, when you do elimination, I want you to think about little Gauss sitting there in first grade. Brilliant mathematician. All right, we've made it to chapter 2. And now things really start to get interesting. So when I asked my Cal 2 class this semester, first day, I was like, so tell me about Cal 1. What's Cal 1 about? The most common answer I got was derivatives. That's what they said. Oh, it's about derivatives. So yes, it is. It's about derivatives. So this is kind of a very, very robust section that we're going to get into now. And 2.1 is kind of where we first start to kind of get a visual idea of what we're going to be trying to do. All right, so there's a lot of pictures here. There's also a lot of formulas, but they're things you should be familiar with. All right, so here we go. Derivatives and rates of change. So first, a very special limit. Okay, we now study a very special limit, which will eventually lead us to the major purpose, one of the major purposes of calculus. This limit that we're going to do is going to be called the derivative. So when you hear derivative, it actually is a limit. It's a special type of limit, all right? And this limit that we're going to call the derivative will help us find the tangent line to any curve. So if someone gives us a curve, we can always find a tangent line. But before we can even talk about that and start getting into like how we can talk about velocities of things and blah, 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 we need to all understand what a tangent line is. So tangent line, if you look at a circle, right? The whole idea behind a tangent line is that if you start with some point on a circle and some other point, you draw a line between those, that is not a tangent line. That line is called a secant line. And now what you do is if you take one of those points and you slide it over on top of the other one, then as soon as you go right on top of the other one, you get your tangent line. So a tangent line to a circle is a line that intersects the circle at one point and one point only. If you move that second point at all, it's no longer a tangent line. Now with circles, there's something really special, and that is if you go from the center out to that point, that's orthogonal, that's 90 degrees. But that's only if you have a circle. What we need to understand is that that line is kind of like just kind of balancing on that curve and passing through one point. All right? That's our notion of a tangent line. So now, let's take that idea and extend it to a function. So let's say I give you a function. There it is. Let's say I give you this point right here, which I'm going to call a base point right there. Okay? And then I pick some other point on the function, and I draw a line through those. That is going to be what we call a secant line. It is a line passing through 2 points. So in terms of your experience with college algebra, if somebody gives you 2 points, everyone in this class should be able to come up with the equation of the line through 2 points. There's a couple of formulas you need. Find the slope, point-slope formula, boom, you can find the equation of the line through 2 points. What about a tangent line, though? What if I ask for the tangent line right there? So what we want to do is, just like we did with the circle, grab that second point and start bringing it closer. But notice it has to follow the curve, right? Like it has to, as it moves closer, it has to follow the curve, and then eventually, as I get really close, let me see here. Let me zoom in a little bit. Zoom in a little bit. There we go. So now I'm getting even closer, 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 and eventually the 2 points are right on top of one another, and you get this tangent line, right? So visually, do you understand the concept of a tangent line? There's no more idea of a circle here. It's not like I'm saying that this only, well, maybe I should say it this way. On a circle, a tangent line will intersect the circle at 1 point and 1 point only, right? Does this tangent line have to hit the graph at just 1 point? I'm going to answer that. No, because it's going to hit it. See this curve? It kept going up. See, it's going to hit it up there? It's only locally, like in this little zoomed in area, that it's going through 1 point and 1 point only. And we also lose the whole concept of this orthogonal, or sorry, I shouldn't use that word, orthogonal 90-degree angle there, okay? We don't have that anymore because we don't have a circle. We don't have a center. But the idea of tangent, does it still make sense?
Yes.
Okay. So that's pretty much the goal, is to see if we can come up with a formula that gives us a tangent line. So it's like right now, if I just say, hey, look, everyone, here's a function, sine x. Okay? We know it looks like this. If I say, hey, go to this point right there, okay? I don't know, maybe that's like pi over 4. What's the tangent line right there? That's what we want to do, all right? We want to do that. It's going to take quite a bit of work to get there, though. All right? Somebody hands you an arbitrary function, gives you a point on the function, and says, give me that tangent line at that point. That's the big picture of what we want to do. Does it sound like it would be hard, or does it sound like it would be easy? Just initially? Easy? Okay. I don't know. All right, so now, this is just recapping. In order to talk about tangent line, we have to start with some point on the curve, right? We have to start with some point. Then we select another point, different from the one we selected first. Draw a line between the 2 points. Slowly move the second point closer to the first one. When the 2 points over on top of each other, we get our tangent line. So now let's do that with more like mathematical symbols behind it. So this is a recap. Remember, if you're given any 2 points, how do we find the slope of the line between 2 points? Rise over run, right? y2 minus y1 over x2 minus x1. Okay? Also, we can find the equation of the line using this formula, point slope formula. Y minus y1 equals m times x minus x1. These should look familiar to you. So let's just, whoa. Let me reevaluate this. This should not all be already opened up. Okay, there we go. Okay, so we know this. Again, this is a recap. If somebody gives you a point, x1, y1, another point, x2, y2, we can draw a line. We can find the rise, which is the difference of the y coordinates. We can find the run, which is the difference of the x coordinates. And then we can find the equation of the line using the formula y minus y1 equals all that, and plug everything in. Everyone in here should, I'm not going to say be an expert in that, but everyone here should mechanically be able to do those things. Now, maybe it's been a while, so it's going to take a little bit to get it going again, but the idea everyone should be okay with. All right. So let's say we have this function here. See it right here? 3x cubed minus 5x. Here it is, polynomial function. Let's say I go to some point right there. Then I grab a second point. And then I draw a line. And then I find the rise and the run. I should be able to come up with that equation, right? I'm not going to go through all those mechanics. Because what we want is a general formula. Right here. This is what we want right here. Let's say I start with the point. Okay, so that point right there is the point A, f of A. I'm going to jot that down over here. So what I'm saying is I'm going to take some point A, and I'm plugging it in, it's going to spit out f of A, right? Whatever that function is, it's going to spit that output out. That's my x1, y1. Then I'm going to pick my second point. My second point can be any point as long as it's not A being plugged in. So we're going to just plug in x. I could have called it B if I wanted to, but we're going to call it x. So my second point is x, f of x, right? So now I've got x1, y1, x2, y2. What is the rise of that? Eventually we want the slope, right? The slope of this line. So if the slope is rise over run, about to pull somebody's name. If the slope is rise over run, Al, you're up. Then what's rise? In terms of these two, what's the rise?
The function.
Okay.
F of x minus f of a.
Okay, so that's your y2 minus y1. Everyone clear with that? F of x. Sorry, I have no idea why I did it like that. F of x minus f of a. Is everyone okay with that? That's y2 minus y1. y2 minus y1. Al, keep going. What's the run?
And the run will be x minus a.
X minus a. Okay? Good. Now, moving along, there's your rise, difference of the f's, and run is the difference of the x's. And that means the slope of the secant line is this. So the slope of the line between those is f of x minus f of a over x minus a. Does that look familiar from something you did in college algebra? We called this something in college algebra. The dump something quotient. It's like the difference quotient, right? Yeah, it's exactly what it is. And the reason you do it there is because they knew you're coming here. Okay, so we've got that, right? Michael? Is it Michael Z? You're up. Okay, so what I want now is if this is the point x1, y1, this is the point x2, y2, then, and this right here is the slope of the line, then the equation of the line, the equation of this purple line should be y equals y1 minus m times x minus x1. That's the formula from college algebra. Let's just replace m with what we have here. Okay, and let's replace x1 and y1 with what we have here. So what would this formula become like?
It would become
Y minus
y minus
f of a
equals f of x minus f of a over x minus a.
of x minus f of a over x minus a. Okay, that's m times
X
minus
minus x.
x1, which is a.
Yeah.
There it is. So x1, y1, x2, y2, plug into that formula, and then use this for your slope. So these are big deals right here. This right here, and this right here. Those are two things you're going to need to know. If somebody gives you an arbitrary function, and they give you some point to start at, you can always find the slope of the secant line between that point and any other point on the graph by using that formula. And you can always find the equation of the line by using that formula. And that's what I summarize here. Right there, there's your slope, right? There's your slope. I say slope, and I subscript it with secant, so that we're talking about between 2 points. And then there's the equation of the line right there. So this is all in your notes, all right? So once we have this, once we have these two formulas, our goal now is to try and figure out how do we get to the tangent line from that formula that we just came up with for the secant line. Because remember, that had 2 points, right? That formula had 2 points. How do we get from from secant to tangent. What do you think you have to do? Look at the picture. First point, second point, draw the line. How do we create the tangent line? So let me ask whoever's up here. Ian. Ian? Ian, no? Ronnie? Ronnie, do you understand my question? Yeah, so like right now we have a formula that would give us not only the slope of this purple line, but the equation of that purple line. How can we go from that to the slope and equation of the line that is tangent, not secant? So like geometrically, what would we have to do to go from secant to tangent? Move one of the points, right? Let's leave this one here. We need to move the blue one. Okay, so when we move it, move it, right? The x-coordinate, this is the x-coordinate, right? This one is A. Ronnie? So Ronnie, as I'm moving that point over, what is happening to that x-coordinate? What is happening to it? It's getting closer to A, right? Everyone see that? What's happening? X is doing what? It's getting closer to A. Okay. And it keeps coming. And X is like, here I come, right? Here I come. And then what happens when we get to here? Eventually, we get there and oh shit. Why is that a problem? Look at your formula. Look at your formula. What was the slope of the secant line? What was it? F of x minus f of a over x minus a. If x actually ever gets to a, right? If it lands on a, then a minus a is 0, and f of a minus f of a is 0. So it's undefined. What we're saying is that it's not possible to find the equation of a line through one point. You have to have 2 points, don't you? And we're trying to get a tangent line by being clever and sliding this over, but as soon as it lands on the other one, everything goes out the door because you can't do 0 divided by 0. Unless you use what? A limit. So even though we can't land that point exactly on top, we can say what it's approaching as x gets closer, right? And we've seen already that when we do limits, we get answers. I mean, does anyone here disagree that that right there has a slope? That purple line has a slope, right? I don't know, would you say it's like maybe it's positive, yes? Would you say maybe it's like up 1 over 2? Maybe the slope is like 1/2, I don't know. And then if I get a little closer, do you agree I still have slope? I still have a positive slope. And as I get closer, it's still positive. And as I get a little bit closer, it's still positive. And I don't know, maybe around there it looks like the slope is maybe, I don't know, up 3 over 1, I don't know, maybe we're at 3 now? So does it make sense to you that if I could land that point on the other one, there's some like limiting sort of slope I'm headed towards? It's not like if I land there, all of a sudden my slope is gonna be like -4. Like if I go just short of it, I'm heading to something, right? I'm heading somewhere around here. Not here, not there, somewhere, right? And this is the thing that calculus allows us to do. The limit allows us to do this. All right, so how do we solve the problem? How do we solve it? How do we solve the problem? If we can't slide, right, Ronnie, we can't slide that x onto A, then we just want x to get close to A without ever getting there? So what do we need to do to our formula right here so that this is defined, Ronnie? Bring out the calculus, right? Which means bring out the what? How do you let something get close to something without actually getting it? You bring the limit out, right? So that's what we're going to do. We're going to say, look, we have a new definition here. If we want to talk about the slope of a tangent line, then what we're going to do is we're going to let x approach a in this formula. We're going to take the limit as x approaches a. So that's this new thing. So this is, we get 0 over 0, right? This is a bad thing. Ronnie was trying to slide a fast one past us there. And we said that's undefined, no good. So we go and the workaround for this 0 over 0 problem is that. Boy, I think I wanted you to see that because I made it kind of big there, yes? We now have a new definition of the slope of the tangent line. The slope of the tangent line should look familiar. It's the same as the slope of the secant line with, oh, I'm over time, with one exception, the limit. Okay, the limit. All right, that's our preview into 2.1. I would not start any homework from 2.1. I would get your continuity homework done. I apologize for keeping y'all late. I guess attendance, I won't do today. No big deal. Have a good weekend. I sent an email out. I'm not going to be on campus tomorrow or Monday, so just check your email. I don't want y'all to show up on Monday in my office hours and I'm not here. So have a great weekend, everyone.
Calculus is